Hi students, Mr. Elpin here. So we're going to go over the rules for oxidation numbers. Up to this point we've been calling them charges, but we're going to switch over to oxidation numbers. And this is important because these oxidation numbers help to know what is being reduced and what's being oxidized. So these are some rules here on the top. And first, let me say, it's not probably the best just to sit down and memorize each of these rules. It's really best to practice. And so I have some practice problems down on the bottom. And you also have a worksheet of homework that you can practice with. So in general, when you have an element that's by itself, it's a zero charge. So whenever you see an element by itself, you can write a little zero on the upper right-hand corner. For group 1 elements, which by the way are the elements all the way over to the left of the periodic table, over here with hydrogen, lithium, sodium, these will have a +1 charge. And then the second group will have a +2 charge. And then as it says in the notes here, over on the right-hand side, group 17 is going to have a -1 charge. 17 is all the way over here with fluorine, chlorine, bromine, iodine. Okay? Beyond that, we don't have a whole lot of rules unless you have a monoatomic like ion where you actually are given a charge, or you have a particular element that you don't know the charge for, they don't tell you, but is on the common ions chart. In this case, like sulfur or phosphorus. In that case, and in the case of the polyatomics, which you see here as a rule right below at the bottom, some of the oxidation numbers for a polyatomic is just the ionic charge. So these are some of the examples here. If you go to the periodic table and then go down, you'll see that these polyatomic ions have charges. You might not have thought of this, but these have particular charges because the charges of the individual elements within that make -1, -2, or -3. So going back to this for a second, the last part of this is that the sum of the oxidation numbers for a neutral compound is 0. And so if you have a compound like on the bottom here, all of these compounds that I gave you are neutral compounds. Not all compounds are neutral, but for our sakes in 10th grade chemistry, we're going to give you just neutral compounds. So that means that all of the charges of each of the individual elements within a molecule are going to add up to 0. So let's go through an example here. Let's go through carbon and hydrogen. So carbon, C2H4, this is ethene. This is going to be a good example. We're going to take a look. First thing is we want to look and see, does this fit any of our rules? And it does. Hydrogen, for example, is a +1 charge. Now, with carbon, we don't really know because there's no rule for group 14, and also that's where it is, by the way. And it's not found in the common ions chart below. So what we have to do is kind of be detectives, and we have to figure it out. And the first thing is it's a +1 charge for each hydrogen. Now, I have 4 hydrogens, so total, that's +4. And I remember this rule, that the sum of the oxidation numbers for a neutral compound, in this case it is because there's no overall charge for the compound, equals 0. So if that's true, then if the hydrogens are +4, then the total carbons, in the case of this is 2, would have to be -4. So we have to think about this. What would each of the individual carbons' charges be in order to make it -4? We have 2 of them, so each of those have to be -2. So those are the charges for the elements in this molecule. For carbon, it's -2. for hydrogen is +1. With chlorine gas, Cl2, notice that it's a single element by itself, right? There's no other elements. It's bonded to itself, that's why it's the subscript 2, but there are no other elements. So elements by themselves have no charge, or zero oxidation number. So KCl. KCl is another good example. With KCl, if you don't remember, you can look at the rules. You can also look at the common ions chart too. So group 1 is +1. Let's see if we have any group 1 elements here. We do. We have potassium, which is element number 19, is in group 1. And then chlorine is over there in group 17, and that's -1. So I'm going to write those charges here. +1, -1. And that's it. Why am I done? Because these add up to 0, right? And so that's good. There's also one of each of them, so we know that we're done. Let's take a look at HNO3. In HNO3, we have to look again at our charges, and we know that hydrogen and oxygen, right, are there. We have to think about the charges. Hydrogen we know is +1, so that's good. We also have to think about oxygen. Oxygen we know is on our common ions chart. It's here. It's a -2. So each of these are a -2. So that's interesting, okay? +1 and then -2, and there are 3 oxygens. So in this case, total for oxygens, it makes it a -6 just from the oxygens. Now, how are we going to figure out nitrogen? What its charge is? Well, I don't see an overall charge for this molecule. It's a neutral compound, so that means that all these oxidation numbers should add up to 0. So +1 -6 equals 0. What does nitrogen have to be? Nitrogen has to be +5. So hydrogen's +1, nitrogen's +5, oxygen's -2. And last but not least, we have calcium chloride. And in this case, again, these are on the common ions chart. So chloride, Cl, is -1. It's also in group number 17, which we know is -1. And calcium is +2. It's also in group number 2, right here. And so we write +2, and then each of these is -1, but there are 2 of them. So total it's a -2. That equals 0, and we're happy. It's really important as a last step that we think and know that we're really looking for these individual element charges and not the total negative charge by the 4 hydrogens being +4 or the 2 carbons being -4. It's really, those are the numbers that we need in order to figure out what the individual elements were. So -1 and +2, or sorry, -2 and +1 in that case. So I'm circling all of the numbers that we really care about. And I'm not circling the ones that we don't. Okay, these will become important when we're seeing them within a redox reaction. We can identify the oxidation numbers because we just did this, and then we can figure out what's being oxidized and reduced. So to recap, one more time, elements by themselves have no charge. Any element in group 1 is +1, in group 2 is +2, and group 17 is -1. Beyond that, if you don't know, you look at the common ions chart for any monoatomic ions like sulfur or phosphorus, they have -2 or -3. Or you look at the common ions chart for the polyatomic ions. All right, so we didn't have any polyatomic examples here, But if we did, you would look for that and you'd write down that charge for that polyatomic ion. And the last step is if you have a neutral compound, which all of the ones that you're going to have will be neutral when they're given to you, you can assume that the charges are going to be added up to 0. That's really important because in the case of, for example, C2H4, we didn't know what the charge was for carbon, and there's no rule for it, and it's not on the common ions chart. So in order to figure that out, we had to know what hydrogen was, multiply that by 4 hydrogens, set that equal to 0, and realize that the carbons had to add up to -4, and that helped us to figure out that each carbon had to be -2 because there were 2 of them, totaling up to a -4 charge for carbons. All right, I hope that was helpful. Take care.